Okay, good morning, everybody. Thanks for tuning in. Today, we're very excited to have Professor Oscar Diaz from University of Southampton. He's going to tell us about strong cosmic censorship. So take it away, Oscar.
Thank you very much, Dan. And in particular, thank you for this kind of opportunity to present this seminar. So what I want to do today is to give an overview or a review of some developments that happened in the recent years about the strong cosmic censorship. And actually, you know, although this is based on work that I have done with Felicity, and with Felicity that was then a PhD student in Cambridge, but nowadays left physics, Harvey and George Santos that are both in Cambridge. You know, I will try that this is a review talk, so I will not just talk about our work. I will try to do an overview of the main developments on this topic, starting with its birth in the 70s with Penrose. So this, hopefully it will be a relatively light talk with not too much technical details, but on the other hand, hopefully I will emphasize the main properties of the systems that are violating the strong cosmic censorship. So the plan of my talk is the following. So I will start by describing strong cosmic censorship when the cosmological constant is 0. So this is basically studies that were done in the 70s, 80s, and 90s. Then I will move on to more recent work that was done on strong cosmic censorship with a positive cosmological constant, namely in the Sitter spacetimes. So the main difference between the two is that strong cosmic censorship basically holds, or a certain version of it holds in asymptotically flat spacetimes, but it can be violated in the Sitter spacetimes. And then I will also mention strong cosmic censorship when we have a negative cosmological constant, namely in anti-de Sitter spacetimes. And here I will tell you that it is preserved typically in anti-de Sitter spacetimes, except when we are in three-dimensional spacetimes. And I will explain the reason why this happens. Now, as you can see, you know, there are cases where the standard formulation of strong cosmic censorship, namely the one that is due to Christodoulou, and that I will detail in the following slides, can be violated. So the next question in the end of the day will be, is there a way to rescue strong cosmic censorship? Meaning, is there a way we can reformulate a version of strong cosmic censorship so that it is always preserved? And the answer will be yes, if we consider quantum effects or a quantum version of the strong cosmic censorship, or if we are willing to consider non-smooth initial data. I don't know if I will have much time to discuss this final topic, but at least I will, if I don't have much time, I will highlight the main message, nevertheless. Okay, so let me move on. So let me start with strong cosmic censorship in asymptotically flat spacetimes. This is a well-established story that happened in the 70s, 80s, 90s. So let me go through it. So the first thing that we should know for this discussion, and that everybody in this room knows for sure, is that when we look at black holes with vanishing cosmological constant, in particular black holes that are solution of the Einstein theory or the Einstein-Maxwell theory, we have two main solutions. One is the Reiser-Nordström that is a static spherically symmetric solution with an electric charge, and the other one is the rotating Kerr black hole. And now an important property of both these solutions is that both of them have an event horizon, and the solution can be extended smoothly across this event horizon. And we say in that case that we move from the outer domain of communications in the black hole to the interior of the black hole. Okay, so here, this is a Penrose diagram for these solutions, and here we have the null infinity. Here we have the past event horizon. Here we have the future event horizon. So these are the boundaries of my outer domain of communications, and then I can extend the solution smoothly to the interior. Okay, another important feature of both these solutions is that both of them have a winner horizon that we call the Cauchy horizon, which is this guy here and here. Okay, and we say that this Cauchy horizon defines the maximal Cauchy development of a Cauchy hypersurface where we can give initial data. So I can give initial data at a prescribed time, t equals to 0. Let's say I give some initial data along this Cauchy hypersurface that I'm calling sigma. And then the maximal Cauchy development is this defined by this triangle, more or less. So this gives the region where I can predict whatever happens in any point of this region. I can predict it by just knowing the initial data that I provide at t equals to 0 at this Cauchy hypersurface. However, beyond this maximal Cauchy development region, whatever happens there, so for example, here, cannot be predicted just by knowing the initial data that I have here at this Cauchy hypersurface. And the reason for this is that, for example, if I have here my event horizon, I have here my null infinity. And if I have this observer that is coming from the outer domain of communications, crossing the event horizon and keeps moving towards the Cauchy horizon, which is here, I see that while I'm in the maximal Cauchy development region, at any point, I can predict what's going to happen there if I prescribe initial data at this Cauchy hypersurface, because I can trace back the null rays from this point, and I see that whatever happens here is a consequence of what I have at t equals to 0 along sigma. However, as time goes on and the observer keeps falling inside the space-time, I see that once I cross this Cauchy horizon here, for example, if I'm at this point here, I see that knowing the initial data is not enough to predict what happens there, because I can also have information that is coming, from this null singularity, or null singularity, no, from this time-like curvature singularity. So initial data here is not enough to predict what will happen there. So this is a worrying failure of determinism in this classical theory, in this classical Einstein or Einstein-Maxwell theory. And actually, this argument led Roger Penrose in the 70s to argue that the Cauchy horizon should be unstable, precisely because we lose this predictivity, we lose this deterministic, we can no longer determine what will happen once we cross it. And the heuristic argument that Roger Penrose gave to argue in favor of this instability was the following. I know that perturbations that enter the black hole from the outside, so that cross the event horizon here, they should suffer what we call an infinite blue shift once they arrive at this Cauchy horizon. And if I have an infinite blue shift, this means that I should have infinite energy densities once I am crossing the Cauchy horizon, or on the verge of crossing the Cauchy horizon. One way of seeing this is we can consider two observers. One observer that is in the outer domain of communications, that's what I'm calling observer A. And we can ask this observer A to send periodically signals to the interior of the black hole, which are these null rays, represented by these null rays. I can also assume that this observer is immortal, meaning that it will live forever. If it will live forever, it will send an infinite number of signals to the interior of the black hole. The energy density is finite, okay, because each signal has a finite energy, but because the observer A lives forever, it will send in the end of the day an infinite amount of energy to the interior of the black hole. Okay, now we can have a second observer that I'm calling observer B that is in the interior of the black hole. And this observer, as time goes by, eventually it will cross the Cauchy horizon. Now, the important thing is that this observer B will receive all the signals that were sent by the observer A in a finite amount of proper time. So, said in other words, he will receive an infinite amount of signals in a finite proper time. This means that he will receive an infinite energy in a finite proper time, and therefore we should have an infinite energy density when observer B is crossing the Cauchy horizon. This suggests, this was the argument of Penrose, that we should have a large back reaction at the Cauchy horizon, because tiny perturbations for A correspond to humongous energy densities for observer B that is in the interior of the black hole crossing the Cauchy horizon. And continuing this line of argument, Penrose further claimed that this suggests that the Cauchy horizon probably will be replaced by a singularity. Okay, it should not be just a null horizon. Okay, and these arguments led Penrose to propose the following conjecture that we know as the strong cosmic censorship conjecture, or at least the C0 version of it, the continuous version of the strong cosmic censorship conjecture, which basically states that if we consider complete asymptotically flat initial data for the Einstein or Einstein-Maxwell equations, then generically, meaning for generic initial data, the resulting solution cannot be extended continuously across the Cauchy horizon. Or said in a more mathematical language, the maximal Cauchy development of a two-ended Cauchy hypersurface should not be extendable, okay, across the Cauchy horizon. Now, if this conjecture is correct, then this would restore predictability, okay? As a side note, I should emphasize that the strong cosmic censorship conjecture of Penrose is completely unrelated to the what we call the weak cosmic censorship conjecture that was also formulated initially by Penrose and then developed by others, that basically states that naked singularities cannot form through or from gravitational collapse. So these two conjectures, although they share a similar name, they are completely independent of each other logically, okay? And in particular, the weak conjecture or the strong conjecture does not imply the weak conjecture, okay? Now, moving on, once we have this conjecture proposed by Penrose, people start thinking on how can I check this conjecture with some actual computations, okay? And in particular, people start looking for linear evidence for the conjecture, okay? And in order to do that, what people consider were linear perturbations around the Rice-Nordstrom black hole and later around the Kerr black hole. So these linear perturbations can be a test scalar field, or it can be some gravito-electromagnetic perturbation of the black hole. Now, an important property of such linear perturbations around the Rice-Nordstrom black hole is that these perturbations, far away from the black hole, as we approach the asymptotic null infinity, they have a power law decay. These are known as the late time tails, or the price late time tails. Actually, these tails are present in at null infinity, but also at the event horizon. And now the key point is that this decay, this power law decay, seems easy enough to trigger the blue shift instability that we discussed previously at the Cauchy horizon. Or said in other words, this inverse power law tails provides initial data for the internal problem for what is going to happen at the Cauchy horizon. And by this, I mean that what I'm going to say next is not a fine-tuned experiment, okay? Said in other words, in order to introduce this blue shift instability at the Cauchy horizon, I don't need to ask my observer A to send an infinite number of signals periodically towards the black hole interior in order to trigger the blue shift instability. Why? Because these tails, these late time tails themselves, they are enough to trigger this blue shift instability. And these tails are present in any perturbation. So this is not a fine-tuned problem. So what is the origin of these late time tails? You can think on it as follows. So you can think, let me go back to the Penrose diagram. So I have here the future null infinity. I have here an observer that is approaching the time-like infinity, I plus. And this, imagine that he sends, or he is perturbed, or there is a perturbation here that sends a signal towards null infinity. This signal, because a black hole spacetime always has a potential barrier, I know that part of this signal will indeed reach infinity, but there is another piece, another contribution that will be reflected at this potential barrier that is around the event horizon of a black hole. And instead of going to null infinity, it will cross the event horizon. Okay? So, or said in other words, if I look at this picture here on the left, I can have here my event horizon. Now, somewhere outside my event horizon, I have a potential barrier that is produced by the mass and eventually the charge and angular momentum of the black hole. And I know that if I have a signal that is sent from near the horizon all the way towards infinity, I know that part of it will indeed scatter through this potential barrier, but part of the signal will be reflected. Okay? And this reflected signal, or the series of reflected signals that I have here, they can provide my initial data here to trigger then the blue shift instability over there. And this is generic. So this will happen no matter what kind of perturbation I have in the outer domain of communications. Okay. Now, as a consequence of these late time tails, what these people, namely McNamara and Chandrasekhar and Hartle, found in the late 70s or early 80s is that indeed a scalar field perturbation, or the gradient of a scalar field perturbation in the outer domain of communications, ends up diverging at the Cauchy horizon, which is what Penrose had in mind. Because if the gradient of the scalar diverges, we know that the energy density of the scalar is basically proportional to the square of the gradient, and therefore the energy density measured by an observer that is crossing the Cauchy horizon will itself be divergent. And therefore, coming back to the original ideas of Penrose, we therefore might expect that if I have a scalar field that is diverging when crossing the Cauchy horizon, it will back react on the gravitational or gravito-electromagnetic field, and it will produce a large back reaction that should ultimately lead to eventually the formation of some kind of curvature singularity. Okay. However, so far I have just given you linear evidence for the strong cosmic censorship conjecture. Now you might ask, do these arguments survive when I go higher order in perturbation theory, when I consider the full nonlinear problem? Is it still true, or could it be that somehow, these linear divergences are cured and nothing wrong happens at the Cauchy horizon? And this is a problem that Poisson and Israel and Dory have looked at in the early 90s. In particular, they consider something that is called the null dust model. So this is not an exact solution of Einstein or Einstein-Maxwell theory, but it is considered to be a very good approximation. So basically, this is a solution in which we have a shell of matter that is following into the black hole, crossing the event horizon into its interior. Okay? And what these authors found is that indeed, at full nonlinear level, there is strong evidence that back reaction causes what we call the invariant Hawking mass, and therefore the energy density, to diverge at the Cauchy horizon. And this is known as, or this phenomenon is known as mass inflation in the literature. So this in particular means that the Cauchy horizon becomes singular. Okay? However, it becomes singular not in the way that Penrose conjecture originally, because Penrose was assuming that the metric itself would become singular at the Cauchy horizon. So, but what these authors have found is that the metric is continuous across the Cauchy horizon. Okay? It's more the derivatives of the metric, or the second derivative of the metric, if you want, that becomes singular. Okay? I should say that, of course, these ideas were developed, I guess that given the audience in this room, you know, these were heuristic computations, if you want, or heuristic arguments, because they were physical computations. But more recently, mathematicians like Mihaly Zafermos, Luke, and O, they have formally or rigorously proven that mass inflation indeed occurs in the Rice-Norton black hole or in the Kerr black hole. Okay? So let me summarize the story up to now. So we have found that the perturbed Rice-Norton black hole, and if you want, this also holds for a Kerr black hole, can be continuously extended across the Cauchy horizon. Therefore, the original formulation of strong cosmic censorship by Penrose, that we call nowadays the C0, the continuous version of the strong cosmic censorship, is clearly false. However, the extension is not class C2. It's not twice differentiable. And therefore, the Riemann, which is involves second derivatives of the metric, will diverge. And therefore, the Cauchy horizon will have a curvature singularity. Which, okay, although this is not exactly what Penrose had in mind, in the end of the day, we get the same desired result, namely that we can predict what will happen, because a curvature singularity appears at the Cauchy horizon, we cannot cross it, okay, in the end of the day, because it's a curvature singularity, and therefore we will not have to worry with what happens after it, okay? However, there is a twist to this story, and this was introduced by Ori in 91. And this twist is the following. He noticed that, yes, I have a curvature singularity. However, if I consider an extended free-falling observer that is approaching the Cauchy horizon, I find that the tidal forces, or the distortions that the observer will find, they do not diverge, they remain bounded. Okay? I would expect, or maybe we would naively expect, that when we have a curvature singularity, if you try to send an observer towards it, you know, this observer will in particular feel infinite tidal forces. But Ori has shown that this is not the case. So we might then ask, what happens to such an observer? But to answer this question, you know, more rigorously, we clearly must satisfy the matter field content of the observer and his equations of motion, or its equations of motion. If these equations of motion make sense in some sense at the Cauchy horizon, then we will still have a problem with predictability. Why? Because the Cauchy horizon has a curvature singularity. Nevertheless, an observer survives it when it crosses this Cauchy horizon. Okay? Essentially because the tidal forces are bounded. Okay? So our the next aim in the community was then to address this question. What happens to an observer that is approaching this Cauchy horizon that has a curvature singularity? What is the matter field content? What are the equations of motion of this observer? Okay, and in particular, the important question here is, what is the minimal regularity condition that we must require in order to make sense of the equations of motion? Okay, and the key observation here is that we can make sense of solutions that are less regular than C2 if we look at weak solutions. One example of weak solutions are shock waves in compressible perfect fluids. I guess that most of the audience is familiar with this notion of weak solutions. Nevertheless, let me quickly describe what a weak solution is, for in case some of you might not be so familiar with this concept. In order to do that, what I want to do is I want to consider Weiss-Norton black hole or a Kerr black hole, and I want to introduce a test scalar field. Clearly, this scalar field obeys the Klein-Gordon equation. Okay, I can solve this Klein-Gordon equation. I get a solution for the scalar field, and the metric and electromagnetic field of the background are considered to be fixed. Okay, at least at linear order in perturbation theory. However, I can extend my perturbation theory to higher order, and in that case, the scalar field that I found at linear order, this first order perturbation, will introduce a source term at second order in perturbation theory that will source a perturbation on the metric field that I'm representing here as H with superscript 2 because it's at second order. Okay, now this second order perturbation on the metric, I also know what is the equation that describes it. Namely, it's the linearized Einstein equation, where on the left-hand side, I have a second order differential operator acting precisely on this metric perturbation at second order that I want to find. And on the right-hand side, I have the energy momentum tensor sourced by this scalar field. This second order differential operator, if I'm looking on a traceless transverse gauge, is the very well-known Lichnerovich operator. The important thing for what follows is that this second order differential operator, because it's a second order, it involves the second derivative of the metric, or the second covariant derivative of the metric, nabla 2. Okay, and these are the equations that describe my perturbation at second order. Notice that in order for this equation to make sense, to be well defined, clearly H2 must be C2, must be twice continuously differentiable, because I'm taking second derivatives of it. And by the way, phi, the scalar field, must be class C1, because this energy momentum tensor involves first derivatives of phi. But now I can do the following exercise. I can multiply this equation by a smooth, compactly supported symmetric tensor, an arbitrary one. Okay, and then I can integrate the resulting equation, and I will do integration by parts. Why do I want to do integration by parts? So I'm doing an integration, and I will do an integration by parts to, as usual, to remove this second order derivative and transfer it to the compactly support field that I have introduced in my system. So clearly, in the end of the day, after integration by parts, I no longer have a second order derivative here, because it was transferred to a derivative of the smooth compactly support tensor. Okay. Now, what is important here with respect to equation number 1 that we had before is that now this equation makes sense even when H2 is not C2. It just needs to be C1. Why? Because now I just have a first derivative there. Okay, so I can have perturbations that do not obey equation number one, because they are not C2. Nevertheless, they obey equation 2 because they are still C1. Okay. Now, if 2 is obeyed for any compactly supported symmetric tensor that I introduce, we say that we have found a weak solution of the original Einstein equation. By the way, guys, the reason why we need that this symmetric tensor as compact support is to avoid the boundary terms when I do integration by parts. Okay, those vanish because this symmetric tensor has compact support. Okay, and in particular, this equation 2, in order for this equation 2 to make sense, we also require that this term here makes sense. And for this term here to make sense, remember, it has this term here is basically the kinetic energy for a scalar field plus eventually some mass term that it might have. Now, so for equation 2 to make sense, we still need that the terms involving the scalar field are finite. And in order for them to be finite, we must require that phi belongs to Sobolev space H1, which is the space of locally square integrable functions, meaning those functions, those fields that if I multiply it by a smooth compact support symmetric tensor, okay, or symmetric, or if I multiply it by a smooth function with compact support, this final field is square integral. Okay, very well. So we have introduced here the notion of weak solution, at least when I'm looking to a scalar field. Then you might say, does this extend if I have pure gravity? And the answer is yes. I can also have weak solutions of the vacuum Einstein equation. Okay. I can repeat the exercise that I did in the previous slide. At second order in perturbation theory, the only difference is that the source that was being sourced by the scalar field now is sourced by the first order metric perturbation. And in the end of the day, I find that weak solutions of the Einstein equation indeed exist, and they do so when we have locally square integral Christoffel symbols in some coordinate chart. Okay. Now, these ideas led Christodoulou in 2009 to reformulate the strong cosmic censorship conjecture. So this reformulation is no longer the C0 version of Penrose, because we already know that the C0 version, strong cosmic censorship version of Penrose is false, because the metric can be extended continuously. So what Christodoulou proposed is, let's reformulate this conjecture in such a way that it is always valid. And this reformulation of Christodoulou states that generically, again for generic initial data, it is not possible to extend the maximal Cauchy development across the Cauchy horizon as a weak metric solution of the equations of motion. Of course, if I cannot extend it as a weak solution, the extension will also not be C2. Okay, and therefore there will also be a curvature singularity. Now, if this Christodoulou version of strong cosmic censorship holds, I get the original final result that Penrose had in mind, namely that predictability is restored. Okay, so gathering, recapping what we have done so far, for zero cosmological constant, in order of the increasing strength, I have at least 3 versions of strong cosmic censorship. One is the original Penrose version, the CNOT version, that states that generically no continuous extension exists across the Cauchy horizon. We now know already that this is false. This conjecture does not hold. And in particular, a rigorous mathematical proof was provided by these authors. Then we have the Christodoulou version that states that generically there is no weak extension across the Cauchy horizon. This version, we know that it is true. It was established by these authors. And finally, we also have the C2 version that states that generically there is no C2 extension, and this is also true. Actually, this one implies the second one. Okay. And here I end, the review of strong cosmic censorship in asymptotical flat spacetime that started with Penrose in the 70s, and we might say that it ended only, if you wish, in 2009 or more recently in 2015, 17, with these rigorous mathematical proofs. Okay, and in the end of the day, the main idea is for asymptotically flat spacetimes, Christodoulou's version of strong cosmic censorship does hold, and therefore there is no way to cross a Cauchy horizon as a weak solution of Einstein equations, and therefore we do not have to worry with what is behind the Cauchy horizon. Now the next question is, and this is work from recent years, from the last 4 or 5 years at most, we might then ask, okay, our universe seems to have a positive cosmological constant. So it's a de Sitter or asymptotically de Sitter space-time. So it makes sense to ask whether strong cosmic censorship also holds when we have a positive cosmological constant. Okay, and this is what I want to address in the rest or in the next slides. Or what is new when I consider the de Sitter space-time? Well, clearly, in the old days when I looked to the Penrose diagram of the solution, I still have the future event horizon, the past event horizon. But now you see what used to be the null, the past null infinity and the future null infinity now becomes a cosmological horizon, what we call the cosmological horizon. So the solution as another horizon, the cosmological horizon. And in particular, the asymptotic region becomes a space-like line. So my infinity is a space-like line. But this means that now if I have an observer that is coming from the outer domain of communications of the black hole, now it can cross the cosmological horizon before reaching infinity. And this means that even if this observer lives forever, that I should have not only the blue shift effect that I had previously here at the Cauchy horizon, but there is also now another effect, which is an opposite effect, is a red shift. And so there is a competition between these two phenomena. I have this red shift because perturbations entering the future event horizon at late time have to climb out to the potential well associated with the cosmological horizon. Now, because I have now this competition between these two effects, I might ask, which one of those two effects will win in the end of the day? Is it still the blue shift effect? If it is, strong cosmic censorship should still be preserved. But what if the red shift ends up winning? In that case, strong cosmic censorship might be violated. Okay? In order to address this, so several authors address these questions, starting with some studies from Meller and Moss in the 90s, and Moss, Brady, and Myers also in the 90s. But more importantly, is this result from the mathematicians Ince and Vasi from 2015. So they looked to perturbations of Reiser-Nordstrom de Sitter black hole and found that these perturbations decay very, very fast. They decay exponentially fast, Recall that for lambda equals to 0, the decay is the price power law decay. Now we don't have a power law decay, we instead have an exponential decay, which is clearly much faster. Okay? And in particular, Ince and Vasi have also shown that the late time behavior of smooth perturbations at the Cauchy horizon is determined by what we call the slowest decaying quasi-normal mode. So the slowest decaying quasi-normal modes have frequencies that are complex numbers, and the late time behavior is dictated by that quasi-normal mode frequency that is the closest one to the real complex axis. Oh, okay. And in particular, we can define something that we call the spectral gap alpha, which is this minimum value of the imaginary part of the frequency, or the absolute value of the imaginary part of the frequency. And what Ince and Vasi have shown is that generic perturbations decay exponentially in time as exponential of minus alpha times t. Okay, where this alpha is the minimum value of the quasi-normal mode frequency. Again, this is to contrast with the power law decay that we have in lambda equals to 0.
Hi, Oscar. If you
Yes.
have a near extremal black hole in de Sitter, does that spectral gap go to 0 for some quasi-normal modes, like it would for Kerr?
That's what I will describe next. That's precisely, in the following slides, I will precisely determine. This is the key question now, right? As you are proposing. What is this gap, right? This will dictate whether, this is enough to trigger the blue shift instability or not at the Cauchy horizon. Okay. And in particular, in order to find if this exponential decay is enough to trigger the blue shift instability or not, the idea is, remember again, right? Remember when a few slides ago I said, hey, look, I don't need an observer to be sending, precise signals towards the observer that is in the interior of the black hole in order to trigger the blue shift instability, because the late time tails, for any generic perturbation, they are enough to trigger this blue shift instability. But now I'm finding that this initial data decays exponentially fast. So it seems that because it decays so fast, maybe it will be not be enough to trigger the blue shift instability. Okay. So, but we will see that in the end of the day, it is still enough to trigger. We will analyze in which conditions it is enough or not. For that, let me consider double null coordinates. Okay, U and V, so that the Cauchy horizon is at V equals to 0. So the Cauchy horizon here in my Penrose diagram is at V equals to 0. Now I can study linear perturbations, generic linear perturbations around this Cauchy horizon, and I find that they are proportional to minus V to a power beta, where this beta is a number that we know very well. Beta is alpha, which is the spectral gap that I defined in the previous slide, so the minimum quasi-normal mode frequency, divided by K minus, where K minus is the surface gravity at the Cauchy horizon. This implies that the gradient of the perturbation, you remember that the gradient was the important quantity to look at when evaluated the Cauchy horizon. It involves, of course, a derivative, so it will decay as minus V to the power B minus 1. And this will blow up at the Cauchy horizon, which is the main property that we want to analyze, if beta is smaller than 1. Therefore, this power beta is the one that dictates which version of the strong cosmic censorship is valid or not in de Sitter spacetimes. Namely, the C2 version of strong cosmic censorship will be valid if and only if beta is smaller than 1. Okay. On the other hand, the Christodoulou version of strong cosmic censorship will be respected if and only if beta is smaller than 1/2. So what does this mean? This means that if in my system, in my black hole system, there is a quasi-normal mode, I just need one, that has beta smaller than 1/2, then I know that my field, my scalar field, cannot be extended across Cauchy horizon as a weak solution. So the Christodoulou version of strong cosmic censorship will be okay. I just need to find one guy, one quasi-normal mode among the many that are out there that does this job. Why? Because generic initial data will be a sum of perturbations, and one of them will be this one. On the other hand, if all, and here it must be all quasi-norm modes have beta greater than 1/2, then strong cosmic censorship might be violated. So the fundamental question now is, what is the value of beta in asymptotically de Sitter spacetimes? Okay, and this is a question that was originally addressed by these authors. So Ince, that I already mentioned, and Cardoso, Costas, Destunis, and Jensen in 2017. They looked at the slowest decaying scalar field quasi-norm mode of Rice and Nordstrom to find beta, and they found that near extreme black holes, beta is always above 1/2 and smaller than 1. This means that scalar field perturbations in Rice and Nordstrom violate the Christodoulou version, although they do preserve the C2 version of strong cosmic censorship. But you might say the following: wait, look, you are talking about a neutral scalar field in a Rice and Nordstrom zeta background. But I cannot form a charged black hole if I don't have charged matter. So yes, okay, the scalar field produces a violation of strong cosmic censorship, but there are other fields. And in particular, the most relevant one for my discussion should be a charged scalar field, because if I form the black hole, I need to have charged matter to form it. So what we decided to do was to add a charged scalar field to our system and see if this charged scalar field could preserve strong cosmic censorship. Okay? Because if I have a sector of matter that preserves it, it should be okay, even if the others do not. Now, we found that beta is very close to 1/2, the critical value of 1/2, but it oscillates around 1/2 as we approach extremality. So this is the value of 1/2, and this is the real computation that we did. We see that it's oscillating around 1/2. This means that the Christodoulou version of strong cosmic censorship is violated because I can reach values above 1/2. Okay? So a charged scalar field does not save strong cosmic censorship. Then we decide to do the following. Wait, but okay, I'm working with a scalar field, but scalar field in the end of the day might just be a toy model. I should just look to pure Einstein-Maxwell theory, consider perturbations of this type around Rice and Nordstrom de Sitter, and see what happens. Maybe in that case, we will find that strong cosmic censorship is preserved. However, this is not the case, because we found that if we approach extremality close enough, we always have beta not only bigger than 1/2, but also bigger than 1, and actually bigger than 2. This means that in the gravitational electromagnetic sector, the violation of strong cosmic censorship is even worse than for a scalar field. Why? Because not only the Christodoulou version is violated, but the C2 version is also violated. Okay? Actually, generic perturbations are of class CR, where R can be as big as I want, as smooth. So R being as big as I want, of course, means that I can approach C infinity. Okay? I can get a completely smooth perturbation as long as I approach sufficiently extremality. So the strong cosmic censorship conjecture is really very badly violated for Einstein-Maxwell theory with de Sitter, with a positive cosmological constant, unlike what was happening with lambda equals to 0. Okay? But then you might ask, okay, so far you have been talking about Rice and Nordstrom de Sitter, But look, Nostrum de Sitter is a charged black hole. In our universe, yes, it's a de Sitter universe, but I don't expect, especially near extremal, because what is making strong cosmic censorship get violated is when I look to near extremal solutions, because far away from extremality, beta is smaller than 1/2. I really need to approach extremality in order to see beta crossing that critical value of 1/2 that leads to the Christodoulou violation of strong cosmic censorship. Now, in nature, in our universe, I don't expect to see highly charged black holes because they will discharge. Okay, so maybe, what we should do is look to forget about the charge and let's look to just to the solution, the rotating solution, the most general solution of pure Einstein de Sitter theory, which is the Kerr de Sitter black hole. And let me ask, is there a violation of strong cosmic censorship for near extremal Kerr de Sitter black holes? Remember, I just need to find a quasi-norm mode that has beta smaller than 1/2 in order to guarantee that I cannot extend my solution across the Cauchy horizon as a weak solution, okay? And therefore Christodoulou's strong cosmic censorship conjecture is preserved. So we went looking for one quasi-norm mode that could have this beta smaller than 1. And a family of quasi-norm modes that has such beta is a family of quasi-norm modes that has large angular momentum. By large angular momentum, I mean large azimuthal quantum number m, right? My background as a d by d phi killing vector field, and therefore I can do a Fourier decomposition along this direction, and this introduces this azimuthal quantum number along the equator direction, okay? And if I take m to be very large, I can do a WQV analysis. Actually, the leading order term or contribution of this WQV analysis is described by what we call geometric optics, whereby the properties of the quasi-norm modes are basically related with null geodesics at fixed radius that we call a photon sphere. And these photon spheres, they are unstable trajectories in the sense that when we perturb them, they will decay at a rate that is precisely the imaginary part of the associated quasi-norm mode that I want to compute. Doing this, we did this analytical computation, but we also did the full numerical computation to confirm that this geometric optics approximation is a good one. And the truth is that we found that indeed beta for Kerr de Sitter, for gravitational perturbations in Kerr de Sitter, but also for scalar field perturbations in Kerr de Sitter, is smaller than 1/2, no matter how close to extremality I am. So Christodoulou's version of strong cosmic censorship is respected by Kerr de Sitter, although it is violated in Einstein-Maxwell theory, in Nostrum de Sitter. Okay, this was a surprise to us because we would expect that Kerr de Sitter would have the similar features as the Nostrum de Sitter. Now, I have 5 minutes. Is this correct then?
Yeah, but don't rush. You can go a little bit over.
Okay, but I think that I will skip the fourth part, but I will discuss the ADS case. The ADS case is not as long as the Sitter. The Sitter was the most important case. But now, to be complete, let me also tell you what happens for a negative cosmological constant, namely if I have asymptotically anti-de Sitter spacetimes. In that case, you remember for lambda equals to 0, generic perturbations outside the black hole decay following the power law decay tails of Price. Then for the Sitter black holes, we found that perturbations decay exponentially fast. For the Sitter, for anti-de Sitter, at least in 4 dimensions, they decay, it's the opposite of the Sitter. They decay extremely slowly. By that I mean they decay as 1 over log of t, of time. Clearly much more slowly than the power law decay of lambda equals to 0. And this was found by these two mathematicians. Now, this very slow decay, these authors, Ozegel and Smulevich, have shown that this is due to a phenomenon that is called stable trapping, that probably many of you know, of null geodesics. What does this mean? This means that these are geodesics, null geodesics that orbit the black hole, but are stable to perturbations. If we do a small perturbation, they will stay where they are. Okay. Now it is believed that this extremely slow decay is likely to strengthen the instability at the Cauchy horizon. Okay. In the sense that for lambda equals to 0, we had a power law decay. Strong cosmic censorship was preserved, meaning that there was a blue shift instability at the Cauchy horizon that would impede us from, or an observer from crossing it. Now that I have a decay that is even slower, so remember in anti de Sitter, now what happens is that my null infinity that used to be here, okay, is replaced by a time-like infinity. Okay, I still have the event horizon, and I still have perturbations here that source, initial data here to trigger the infinite blue shift instability when an observer tries to cross the Cauchy horizon. Now, because these perturbations here, they have an extremely slow decay, they should have enough time to source, even more time than in the lambda equals to 0 case, to source a blue shift instability here at the Cauchy horizon. This makes sense. So the Christodoulou version of strong cosmic censorship is expected to be true in ADS. There is no point to do many more computations. Now, what came as a surprise is that the C0 version, yes, the Christodoulou version is expected to be true in ADS, but the C0 version, namely the version due to Penrose, is still false in ADS, as shown by this mathematician, Kelly. Okay? So it is still true that I can cross the Cauchy horizon of an asymptotically ADS black hole continuously. I cannot cross it, in principle, I cannot cross it as a weak solution, neither as a C2 solution. Okay, but I can cross, but the metric is continuous there. Okay, and maybe at least for many of us, this came as a surprise. Okay. Now, what I said till now is true for ADS in 4 space-time dimensions. But now I want to look to the d equals to 3 case. The d equals to 3 case, even with a negative cosmological constant, the story is completely different. And why? Mainly because stable trapping is not present for this dimension, d equals to 3. There is no stable trapping. And this means that the generic perturbations, instead of decaying as 1 over log of t, actually they decay very fastly, exponentially fastly, very much like in the Sitter case. We recognize here the exponential of minus the spectral gap times t. So this clearly is inviting us to say, oh, probably this guy, black holes in ADS black holes in 3 dimensions, probably they will violate strong cosmic censorship very much like Kerr did. Oh, sorry, black holes did in the Sitter. Well, we have to be careful here, right? Because in the Sitter, actually, it depends on whether I'm looking to gravitational perturbations or scalar field perturbations, right? Gravitational perturbations did not violate strong cosmic censorship in Kerr, the Sitter, neither scalar field perturbations. Now, what I'm proposing here is let's look to the analog of the Kerr, the Sitter black hole, but now in ADS, not the Sitter, and in 3 dimensions. This black hole, perturbations in this black hole also decay exponentially. Could it be that nevertheless, that although they decay very fast, or because they decay so fast, they will manage to violate strong cosmic censorship or not. In Kerr de Sitter, this was not enough. What about three-dimensional asymptotic anti-de Sitter black holes? By the way, these asymptotically anti-de Sitter black holes in 3 dimensions are known as the BTZ black holes, Barnard, Stadelbaum, Zanelli black holes.
Oscar, is there a way to see that there's not polynomial decay? Why is it automatically exponential?
Well, the way I would say, the best way I would say would be this one, to explain why there is such a difference with d equals to 4. Stable trapping was really fundamental to find this decay here. You know, these authors have emphasized this really very well. Okay.
Mm-hmm.
Now this feature, this feature of stable trapping is not present in d equals to 3. So at least we know that it should not be like this one.
Mm-hmm.
Of course, this does not explain why it is exponential and not power law, for example. Okay. And that, you know, I don't have a straightforward, short heuristic argument to explain why that is the case. Okay. But it is the case of.
I see. So it's proven, but there's no like nice physics explanation for why that is.
It's proven. It's that I don't have an heuristical physical explanation besides this one.
Okay.
You know, because you have in d equals to 4, you have stable trapping, right? Which means that, you remember that quasi-normal modes in the end of, or perturbations in the end of the day, they are related to the decay rate of null geodesic when you do a small perturbation of it. And the fact that you have stable trapping means that if you perturb this geodesic, it stays where it is. So the fact that in d equals to 3, you don't have this anymore is making this huge difference. But, you know, at least now, you know, while without, you know, revisiting these papers of Ozagel and Smulevich, you know, I don't have, you know, a short, sharp physical argument or heuristic argument to make us see why it is exponentially fast and not power law, for example. Okay.
Thanks.
So what we decided to do is to do the real experiment. So we start, you know, so far, you know, I have been looking at the Cauchy hypersurface that was time-like, that was space-like, sorry. But actually we can provide initial data. In my anti-de Sitter black hole, I can provide initial data along a null Cauchy hypersurface that is made of the event horizon, the past event horizon, and the time-like boundary. So I put some smooth initial perturbation along the null horizons and along the time-like boundary, and I let these perturbations evolve, cross the event horizon, and approach the Cauchy horizon. Okay? And when we do this, we find that, again, very close to extremality, we always need to go close to extremality, we can find that our scalar field can always be of class Ck, where K can be as big as we want, as long as a certain quantity beta is bigger than K. And this beta is what? This beta is a quantity that is related to the mass of the scalar field, that for those of you that are familiar with ADS CFT or holography, this is the conformal dimension of the operator. So it is related with the mass of the scalar field and the ADS radius, like by this relation here. Okay. But this is, so this is a fixed quantity. Once I fix my theory, I fix my scalar field, it has a precise mass. So this is a finite number that is fixed. But then here in the denominator, you see that we have a quantity that can be as small as small as I want. Okay, so here this is the event horizon radius, this is the Cauchy horizon radius, and you see that at extremality r plus goes to r minus, and so in the limit where I approach extremality, the denominator becomes 0, which means that beta can be as large as I want. And if beta is as large as I want, my scalar field will be class CK, where K can be as large as I want, as long as I'm sufficiently close to extremality. This means that strong cosmic censorship, be it the Christodoulou, the C2 version, or the C3, C4, C5, whatever version you want to call, is violated in this BTZ black hole. Very badly violated. Okay, in spite of the fact that we are in anti-de-Sitter. And now probably I should speed up a little bit. Then give me a number. How much more time?
Could you finish reasonably in 3 or 4 minutes? Is that enough?
Okay, I shall do so. Let me just, before I finish this BTZ case, let me just say that this result for BTZ relies on an amazing coincidence. What is this coincidence? As in the de Sitter case, the analysis reduces to considering quasi-norm modes of BTZ black holes. And in particular, you know, the one with the slowest decay, right? The one whose frequency was closest to the real axis in the complex plane. Now, there happen to be two classes of quasi-norm modes. One is the modes that co-rotate with the black hole, and the other family are the counter-rotating black holes. Now, the ones that usually are relevant for strong cosmic censorship are the co-rotating black holes. But the co-rotating black holes frequencies, in this particular BTZ case, and only here, and this is something that we do analytically, okay, we don't even need numerics, so it's a precise coincidence, okay, coincides with the frequency of another class of quasi-norm modes that live in the black hole interior. These correspond to perturbations. I look to the interior of the black hole and I consider perturbations that have this boundary condition, outgoing at the Cauchy horizon and the ingoing at the event horizon. I can look at this problem. I forget where this comes from. You know, of course, for astrophysical reasons, we do not care about this class of eigenvalue problems, but mathematically I can solve this problem. It's an eigenvalue problem, you know, defined on this domain with these boundary conditions. And it turns out that the quantization of the frequencies in this problem is gives precisely the same frequencies as the standard quasi-norm mode problem in the outer domain of communications. And this is very important because when we are doing the computation to analyze the smoothness level of a perturbation when it reaches the Cauchy horizon, basically we have a pole, okay, let me call it like this, in our computation. This pole would make, you know, this co-rotating black quasi-norm mode be the dominant one for the computation. But it turns out that because of these quasi-norm modes, interior quasi-norm modes, I have another quantity that is called omega minus omega star, but let me call it tilde. These are the interior ones, okay? And in standard black holes, this omega tilde is different from omega, okay? But it just happens that here in BTZ, the omega tilde is the same as omega. And therefore, if you want, this pole is canceled by this 0. And this means that the co-rotating black hole disappears from our discussion. And from now on, the class of quasi-norm modes that matters to discuss strong cosmic censorship becomes the counter-rotating quasi-norm modes. Now, the important is that the non-smoothness now is dictated by these counter-rotating black holes, quasi-norm modes, and they have enhanced differentiability near extremality, which means that strong cosmic censorship ends up being very badly violated in BTZ. Okay, and now to wrap up, let me just say, okay, we have found cases in de Sitter and even in anti-de Sitter where strong cosmic censorship, be it even the best one that we have, the best formulation that we have, which is the Christodoulou version, is violated. So our next task is, okay, we already faced something like this in the past. Christodoulou noticed that the Penrose formulation of strong cosmic censorship was violated, and then he proposed a new version, a new reformulation that holds. Maybe we can do the same now. So what can we do to try to save it? There are two ways at least. One is through quantum effects, and the other one is by considering non-smooth initial data. Let me briefly mention the quantum effects. The quantum effects, basically what they state is that once I consider quantum effects in my perturbations and I compute the energy momentum tensor associated with these quantum effects, typically I find that the expectation value of the energy momentum tensor associated with these quantum effects diverges at the Cauchy horizon. Okay, now it's not the classical energy momentum tensor of the scalar field that is diverging at the Cauchy horizon because the gradient of the scalar field is diverging at the Cauchy horizon, but it's the quantum version of this, which is the energy momentum tensor, or the expectation value of the energy momentum tensor associated with vacuum polarization, because it's a quantum effect, does diverge at the Cauchy horizon. So at the pure classical level, strong cosmic censorship does not hold, but when we include quantum effects, it does hold, in most of the cases at least. Okay. There is a special case, which is BTZ, where this is not true, but this is only if we look at the linear level. Once we include back reaction, in the end of the day, we see that strong cosmic censorship, the quantum version of it, also holds. Just very briefly, there is another way, something that was proposed by da Fermos, by mathematicians da Fermos, that for sure you know, these two guys. And they said, hey, look, so far you have been considering only smooth initial data. What if you consider rough initial data? Maybe in that sense, in that case, strong cosmic censorship will be preserved. But then you might say, wait, yeah, but this is what I expect, right? If I start with non-smooth initial data at my Cauchy hypersurface at t equals to 0, what do I expect? If I start with crap, as time evolves, I will get crap also at the Cauchy horizon. So this does not seem to be very surprised. Yeah, but what these guys have shown is that, yes, but if you start with rough initial data, the degree of smoothness gets even worse when you reach the Cauchy horizon. And in that sense, strong cosmic censorship is being preserved because you are decreasing the level of smoothness. And I should stop here. I guess I just leave you with a brief summary of what I just said. So strong cosmic censorship basically is the statement that physics should be predictable from initial data. This is very likely to be true for ADS and asymptotically flat black holes. And it is certainly true for pure Einstein theory in the Sitter spacetimes, but is very badly violated in pure Einstein-Maxwell theory when we have a de Sitter universe. Okay. And in the end of the day, quantum effects or non-smooth initial data can save the day. Okay. And I stop here.
Okay, let's all thank Oscar for a fantastic, very clear talk. We have time for questions, so if you have one, just unmute yourself. Go ahead.
And just to be clear, what are you seeing now? Now you are seeing probably my Zoom screen, right?
Yeah, it just says you were
Okay.
sharing.
Yeah.
I have a question.
Yeah.
You talked about the photon sphere quasi-normal modes being related to the properties of the circular photon orbits. And my question is, sorry?
It was not me that said something. It was someone else.
Okay, in the slide where you were showing about the quasi-normal modes and the photon sphere.
Correct, this one.
Oh, yeah, and I was also looking at this article where you say that the photon sphere quasi-normal modes are related to the properties of the circular photon orbits. My question was, can they also have the properties of the photon orbits that are not circular, like the ones which are not confined on the equatorial plane?
Yes, I think that this family of quasi-normal modes, there is another family of photon spheres of geodesics that are not along the equatorial plane, that also describe another class of quasi-normal modes in Kerr that are not these photon spheres.
Okay.
But I don't remember the exact details, but I can tell you the reference that discusses this. You know, the point is that when you look to quasi-normal modes in black holes, you don't have just one family of them, and by one family, of course, you have the overtones, right? You have a tower of quasi-normal modes starting from the one with the lowest frequency, which is described by the overtones. So for a given set of quantum numbers, if you have some spherical harmonic decomposition in your system, for example, you have L and M, okay? But then you also have the radial overtone that basically gives you the number of zeros along the radial direction. And if you want, tells you where the perturbations are localized, if they are localized at smaller radius or at larger radius, okay? So I'm considering all of these as a single family, okay? But then you have what is called the photon sphere modes that have this geometric optic description, in the sense that in the iconal limit is m goes to infinity. This is in a sense a particle limit, okay? These are the photon sphere modes. If you want, these photon sphere modes, they come from literally a WQV analysis of your perturbation equation, your perturbation ODE or PDE, okay? In the limit where m goes to infinity, okay? And this WQV analysis, of course, it's an expansion in 1 over m, okay? And the leading term of this expansion coincides, this is really a nice result, with an analysis of geodesics along the equatorial plane. But then there are at least another family that is quite often in black holes that have an extremal configuration, is what is called the near horizon or the near extreme family. These are typically black hole quasi-normal modes whose imaginary part of the frequency goes to 0 at extremality. So let me put it like this: when R goes to R plus or T goes to 0, okay? So, which is not the case of the photon sphere modes. And this family, there is an article from Emmanuel Berti, plus Zimmerman, and now I'm missing, and then it's, I think, Shang, or maybe Zhang, sorry for that. You know, I can send you the precise reference from 4 or 5 years ago that discussed the connection between this family, this near horizon family of quasi-normal modes, and the geodesics that are not along the equatorial plane, okay?
Oh,
if you want to send me an email, you know, I can then forward, send you this precise reference, okay? Oh, sorry,
sure, thank you.
I missed this one. And by the way, if you are in the Sitter spacetimes, there is a third family, which is called the Sitter family, which is a family of quasi-normal modes that in the limit where the mass, the angular momentum goes to 0, it coincides with a normal mode of the Sitter. The Sitter, you know, has normal modes, you know, and then when you turn on mass and angular momentum, you know, the frequency moves in the complex plane that you can make. But this third family is completely different from the other two.
Okay, thank you for the explanation.
I have a question. I'm wondering if your analysis is relevant at all for strong cosmic censorship in Spacetimes with compact Cauchy with compact Cauchy surfaces, so not with spacetime, not black hole spacetimes. Is it relevant for these other studies of strong cosmic censorship?
Okay, I'm sorry, I don't think that I got your question. So I picked the word compact Cauchy surfaces.
No, compact Cauchy, yeah, compact Cauchy surface. There are spacetimes with compact Cauchy surfaces in which strong cosmic censorship has been addressed. No black holes. I'm wondering what if your analysis is relevant to
But,
that study at all.
but if you don't have a black hole, you don't have the Cauchy horizon, right? And you don't even have the
Oh,
event horizon.
that's not correct. You could have a Cauchy horizon.
Ah, okay,
Like for
okay. You
example,
are thinking,
like
okay.
Tom Nut, things like that.
No, look, sorry. You can have, for example, the Sitter spacetime that has a cosmological horizon and does not have a black hole. For example, this is, the most evident one. Yeah, you can consider spacetimes that have some kind of horizon. No, as far as I know, but don't trust me because I don't know very much. Okay, as far as I know, it was not considered in other contexts, but I might be missing something. I would say a good literature review of this subject starting in the 70s, 80s, and I don't remember, seeing a discussion in that context. And then in more recent years, I did not see such a discussion.
Well, I could send references to you if you'd like.
So you are saying that there are studies done?
Sure.
In that case. Okay, I would appreciate very much indeed.
Okay.
Please do so.
Okay.
Thank you.
Thank you. Thanks.
So Oscar, it seems like almost all of your examples involve near extremal black holes. Sometimes those black holes actually have an instability on the outside of the horizon,
You
like
are
Arcticus instability, that sort of thing.
Takis.
Generally expected that just kind of keeps them from being purely extremal. And I was wondering if that, if that's putting some bound on the spectral gap just because you can't get precisely to extremality, whether or not that.
Yeah, so the question is, in order to discuss strong cosmic censorship, we cannot say, oh, strong cosmic censorship is preserved as long as I'm not too close to extremality, and then it is violated when I'm close to extremality, right? You have the Weiss-Norton or the Kerr family, and it includes the full phase diagram. So, when you say whether it is preserved or not in a given space-time, you have to consider the full phase space. What we have found is that the region that is critical when there is a violation, the region that makes it be violated occurs near extremality. Now you might say, how near to extremality do I need to be? Sufficiently near, but it's not that you have to be extremely near in some cases, okay? So you might say, okay, there is the Takis instability that will probably make the system drive away from extremality. Yes, but it might drive away from extremality, but still be sufficiently close to extremality that strong cosmic censorship is still being violated, okay? And that I cannot tell you whether this is the case or not, because we never did a time evolution, let's say, of the Takis instability to see where you end up, right? The other thing that I can also say is that there are also studies that show what happens, if you start with a charge, you start with a space-time, a black hole space-time that has naively a Cauchy horizon, and then you send, an observer into the interior of the black hole. So you make the observer cross the event horizon and then approach the Cauchy horizon. And interestingly, what you find, at least in certain theories, but you need, for example, to have a scalar field in order for this to happen. So this does not happen in pure Weiss-Norton. the theta, okay, you need to add a scalar field to it. What you can see that happens is that as you cross the event horizon, you can see very well the time evolution of the system, and in particular, you see that in the region where you would expect the Cauchy horizon to form at late times, you see clear evidence for the formation of a null singularity. So you start with a space-time, you see, that has naively a Cauchy horizon. But when you cross it, the event horizon, by crossing it, I mean you perturb the system, you know, your theory as in addition a scalar field. And you see how the scalar field evolves. You find the solution of the Einstein equations in the interior of the event horizon. And remember, once you are in the interior of the event horizon, R becomes time, right? A time coordinate, okay? What you find is that deep in the interior, where you would expect the Cauchy horizon to appear, so a null hypersurface, what you find is that there is a null curvature that develops there. So you remove completely the Cauchy horizon from your system. I don't know if this. So this is to give you another example of something that might drive you away from the question, why do, if there is no Cauchy horizon, right? In the end of the day, I don't have to worry whether I can cross it or not. One way of it is the attack's instability, right? If it drives you sufficiently far from extremality. But there is this other way, you know, when you consider certain kind of black holes that naively would have, you know, for example, Rice-Nordstrom, the theta, it would naively have, or until the theta, or would naively have a Cauchy horizon. Once you put a scalar field perturbation, you find that this Cauchy horizon becomes, or the would-be Cauchy horizon is replaced by a null singularity.
I see. I guess one other related question I would have, there's these interesting papers recently about the instability of the quasi-normal mode spectrum, at least for asymptotically flat black holes, these pseudo-spectrum papers where they show that if you do some small perturbation to the potential, it can dramatically change the quasi-normal mode spectrum.
So I'm not familiar with them. So could you explain? So what are you doing? You are deforming what?
Yeah, the idea is just that sort of in non-Hermitian problems like the quasi-normal mode boundary condition.
You change slightly the boundary condition. That's
yeah,
it?
basically the changes in the spectrum aren't really bounded by changes in the potential, for instance. So you could do a very small change to the potential, like add some perturbation outside the black hole, and then the quasi-normal mode spectrum just reacts in some crazy way.
So it's not a small perturbation of the original.
Yeah, and but I guess I think that usually doesn't affect like the very lowest lying quasi-normal mode, which is really the only one that you're using for these violations, right?
On the other hand, I guess that this is in the context of ADS black holes, or I'm just trying to understand why you would like to change your boundary conditions, right? Because the boundary conditions in the quasi-normal.
Oh, it's not a change in the boundary conditions, but if you just imagine if there's some small perturbation to the Kerr geometry, it could be like some other small linear perturbation.
Okay, is the space-time as a whole. Okay,
yeah.
The space-time as a whole. What could I say in that case? I would say, yeah, I guess that, okay, first of all, I don't know, okay? I never did any computation along those lines in a slightly different space-time, but I would say that the main feature of strong cosmic censorship should not be that much dependent on the fact that the quasi-normal mode spectrum changes dramatically. In the sense that you remember, in your computation at a certain point, what you have is a pole. You have something like 1 over omega minus omega star. I don't really care if this omega star is this number or a completely different one. The pole will be there, generically. The only critical situation is if there is then this pole is being multiplied by another term that can cancel it. But this seems to be very unique to BTZ. We never saw any other solution that has it. And actually, we even suspect that this is because, BTZ, perturbations in BTZ are really described by hypergeometric functions or hypergeometric equations instead of being the generic coin one. Okay, so this is very unique to this case. So, if you consider a generic deformation of Kerr or Weiss-Nordstrom, I doubt that you will get, a zero that will cancel a pole. So that would be, my bet. Okay, it should not change dramatically the results, but in the end of the day, look, for example, for the theta, right? You have to do in the end of the day the actual computation, find the spectral gap, and then see is it smaller or not than 1/2, right? And then we saw, depending on the sector of perturbations we look at, it can be or it might not be. So I think that in the end of the day, you would really need to do the computation instead of betting from scratch.
Yeah. Okay, great. Well, I think we're quite a bit over time, so I'll end the recording now.